we should not write it as delta width. This should write it as half beam width.
Okay.
Yeah. So because delta S we were using it to denote the distance between main lobe and grading lobe. So from there we know delta S is 1 over delta U, right?
Which is the distance between the main,
Yep.
the peak of the grading lobe and the peak
Yep.
of the main lobe.
And then we also know delta U is basically delta L over lambda,
Mm-hmm.
and delta L is L over n element.
Sure.
Right. Wait, should we it should be n minus 1, because if you have only 2 elements. No.
Depends. Like, am I
Yeah,
gonna put them
depends
here,
how you put it.
or
Yeah.
am I gonna put them like here?
I think
L is fixed, so you assume them at the extremities, right?
I think you don't put it at extremities.
You know.
So
You've been doing like the whole problem because L is 1 meter.
Yeah.
If you do not do that,
if you have 2 sources, how do you place them?
no, I mean, like away from this, I thought that like the whole prompt assumed that you would like still have them at 1 meter.
Well,
Yeah.
no, but I like use that 1 meter to find n. So that wasn't. It didn't go that direction. I don't think. Like, you didn't start with 1 meter with. Keep going.
Okay. I think here is actually the question. We know the door width is 1 meter. You can only put the 2 sources within that range. Where would you put so you have the best steering angle? So apparently, as we see here, the half beam width is not determined by delta U, like the distance between the 2 elements. But angular resolution delta S is determined by delta U. We want a bigger delta U, smaller delta U, so that we have a larger delta S.
Yeah.
To have a smaller delta U, we just put the 2 sources closer. Then the ideal case is that when the 2 sources are like really close to each other.
In that case, I have no grading loops. Wait a minute. Yeah. I
In
got
that
lots.
case, you can steer a large angle without
Oh.
grading lobe show up in real space.
Okay. Yes.
Yeah. Is that what we can do though, or we have to fix it? We probably have to fix it at these 2 endpoints.
Are you asking what is the question asking?
Okay, the question is asking that like now, given Q3, that we know 2 elements gives us the best beam width. Now the question is how much we can steer before making grading lobes show up in real space.
I think that it would want. I mean, like in real life, you'd want the worst case scenario,
Yeah.
right? Which is them at the extreme, even if it's not real.
Yep.
So there's one thing. The 2 elements should be at the end, as Pedro was saying, because otherwise the equivalent array, continuous array size, L, will be shorter. If you only have 2 elements, then if I place them here, the equivalent being array size is probably that's like 1 foot. If I put this much, then it's 2 foot. 2 feet. If it's 1 meter, which is 3 feet, it's like it has to be placed this far apart because this won't become a 1 feet long array. Instead, only it has to be like that. So that tells us the delta U, which is basically the size of that, and then we can calculate how much angle we can steer with delta S.
Can I just like follow up question?
Yeah.
So how does this relate, for instance, to what you were saying about sampling? Right, because for instance, in this case, you have L, which is, what? Yeah, I guess, yeah, because your L will be like 10 times greater than your wavelength, right?
Yes. Wavelength is like probably 0.1 meters.
Yeah.
And L, since L is a lot bigger than wavelength, what that I think to answer your question here, for basically the size of array compared to the wavelength if it's if the size of the array is much bigger than the wavelength, which is this case, then we'll see a clear beaming pattern. If it's smaller than wavelength, at a distance that's about on the magnitude of the wavelength away, what we see is it's like point source. So regardless, don't think it as an array. Think about it like it's a source of certain size, of size L. If the size of the source is smaller compared to the wavelength, and we are standing a distance about the wavelength away, then it looks like a point source to us.
Sure. Maybe can we go through like for this particular example when aliasing would occur?
Oh yeah. Aliens.
Yeah, we get this.
So basically, it's when the spatial resolution, spatial.
Well, you'd always have. Oh no, yeah, you have aliasing. There's probably like a set of angles for which you don't have aliasing, right? Because for instance, if I have, there's a set of angles for which the difference between so for the same wavefront, I get less than a wavelength of difference between the same wavefront hitting the two transducers, right?
You mean less than a pi over 4?
I was actually talking about like a one wavelength, right? Because if you have, for instance, if it goes this way, you have the same wavelength. If it goes this way, you actually will have something like 10 wavelengths between them, right?
Goes one way.
So like when the waves are propagating along this direction in parallel to the array, then you will have 10.
Oh yeah, and I'll have
crests as well. Let's think about it. What does the aliasing mean? Aliasing basically means that you have grading lobes within your scope, within your scanning range. Grading lobe is like the equivalent. They have same magnitude as the main lobe. So what that means, what that equivalent to, I think that you can think about it in a real case where you have a sensor, like a bunch of sensors here, and I'm walking by here, that there's some kind of sound waves bouncing off me that's being received by these arrays, and if that, if there's grading lobes, there can be grading lobes in range. Then you couldn't tell if I am at the main lobe position or the grading lobe position. Is that right? Probably not right.
Why don't we just watch what happens? So, if we have grading lobes in real space, that means that the delta U is what? Less than 1/2? Greater than 1/2? Delta U needs to be smaller. So it's less than 2.
Yeah.
Right? Carry around, right?
So you can see this way, there are grading lobes.
Large delta U, that's when you bring up the grading lobes into real space.
I meant 1 over delta U.
Yeah.
Yeah.
So.
Oh, I think I understand what you're saying. It may be so that. Remember when we had this discussion about like the compact source, relation between compact source and wavelength, as in being like the whole pressure varying, right? So when it's like a small wavelength, you'll feel like the small variations of interference between those two, right?
Yeah.
Whereas with a large wavelength that's much larger than L, you still see pretty much the same wave going through them.
Yeah. If you think like a long way, that you don't see much interference between them because the wavelength is so long, and the distance between the two sources are very small compared to the wavelength. So if they are emitting at the same time, there is not much interference between them.
Oh, I think I understand. Can I try to drive?
Yeah.
Okay. So, and I agree that it's a lot easier to see for those. So, if these points are close together, and this is a delta Z, but it is proportional to my delta U.
Yes.
So, say this goes like delta. And if I have a very long wavelength here, lambda much greater than delta delta U because I think delta U is just normalized by lambda anyway.
Yeah,
That's probably why. Actually, is that the signal between these two will be received pretty much at the same time, compared to having. That's probably exactly why delta U is normalized by lambda. I have lambda, which is much less than my delta U. I'm going to get exactly what aliasing is, which is a frequency that I pick up, which is going to be lower than the actual frequency of the wave. Because if this is the actual frequency, and I have aliasing, I'll pick up more than one wavelength away. This. And then I'll get this wave out of it when this happens.
I think that's good explanation.
Cool.
I just didn't understand your lambda there.
My lambda?
That lambda there.
That's the lambda, right? Oh no, that's K. Sorry, guys.
No, not at all. Just kidding.
Well, that's still K, right? It's at least in the right direction.
No.
Why is that not K? K is wavelengths per what?
K is 2 pi over lambda.
Yeah, it's still in the same direction. Why is your K orthogonal?
It's orthogonal to the wave propagation direction.
But your wave is propagating
That way.
Oh, I see how you guys are looking at it. I have water waves, I guess, in my head. That's not working.
Oh, so you're like just drawing displacement?
I don't know what I was drawing. We can do that.
Yeah, so you're sampling, you're really like sampling completely different waves, so that brings up aliasing.
Yeah.
Cool.
Good thing we went over this.
So this is our first exercise of the night. That we went over some of the resolution, green lobe stuff. Then now let's do some fun Fourier transform and convolution.
Stop that.